Hey, this is Walt with a video covering my implementation of an Arduino temperature monitor. This project will wait for temperature to stabilize and then record temperature readings every 10 seconds for 5 minutes. It then waits for a button press and records temperature at the same interval for another 5 minutes. It uses a round robin with interrupts designed to accomplish this. First, I'll talk about the high level functionality, then dive deeper into configuring a timer interrupt, implementing a storage class using EEPROM, and finally interacting with the temperature sensor. Here in the setup function, I initialize the pin mode for the button and an LED to indicate that the Arduino is waiting for a button press. The storage and timer are then initialized, but I'll cover those in more depth here shortly. In the main loop function, this logic handles pausing, restarting, and terminating storage of temperature data. After 10 total minutes of records have occurred, no more data should be stored, so the function immediately returns. After just 5 minutes of data have been recorded, the LEDs turned on and we wait for the button to be pressed. After this happens, more data is recorded. A flag is used to allow the interrupt service routine to tell the task code that a new temperature reading should be taken. To prevent issues with this piece of shared data, the task code disables interrupts before and after reading or writing that flag. When it's true, we take a new reading. This snippet of code just prints the current temperature and stores the data when necessary. The recording's variable is incremented so the previous logic knows when to pause, restart, and stop recording data. Before any data is recorded, we have to detect when the temperature has stabilized. To do this, we record the last seen temperature to compare it against the current temperature. If they're the same, then we consider the temperature to have stabilized and the recording of data is enabled. I use the timer 1 timer to configure a periodic interrupt every 1 second. This requires configuring the timer through a few registers, the first of which is TCCR1A. Although this register is basically left alone, I used port A on this timer, so had to ensure that it was enabled by setting the high 2 bits to 0. TCCR1B, on the other hand, does require specific configuration. I decided to use a prescaler value of 256, so the low 3 bits are set accordingly. The Atmel manual suggests using the capture noise canceller, which is enabled by setting the high bit to 1. The OCR1A register contains the top value of the timer when configured the way I've done. The manual provides this equation for determining what value should be assigned based on the desired interrupt frequency. I wanted an interrupt every second, which means a frequency of 1 Hz. As you can see from my comments, the equation I used gave a frequency of 2 Hz, as I was using the waveform frequency equation. However, I should have used the pulse width modulation equation, which gave me the value here in pink. Finally, the time mask register needs to be configured to output the compare A match interrupt, which is the interrupt triggered when the timer reaches the value assigned in the previous register. This is the interrupt service routine called for that interrupt, and it uses a counter to determine when the flag should be set. Since this interrupt is driven every second, we count up to 10 and then set the flag. Now on to the storage template class. A template is used so you can create a storage class specific to the type of data you like to store. In this case, we wanted to store floats. It tracks the size of the region, where it begins, the current working address, and a default value which we'll see used here in a moment. The underlying storage uses the Arduino's built-in EEPROM. First, we need to ensure that the requested amount of storage doesn't exceed what's available. Next, it looks in storage to see if any existing data is there and prints it out in CSV format over the serial connection. There is other code which prompts the user to type Y or N to clear storage, timing out with a default answer of N for no. If storage is cleared, then we loop over the specified area and write the default value into it. The write function takes a single piece of data and writes it to the current working address. This address gets updated, wrapping around to the beginning if we reach the boundaries of the requested region. The temperature monitor class handles reading and retrieving temperature data. It must know the type of sensor and to which pin it's connected. I then use the underlying DHT library to interact with the sensor itself. The only real work performed by the constructor is to initialize the DHT object with the given pin and type and then start the object. The update function is called when a new reading should be taken. This code creates a new DHT event and reads the temperature from it, storing the appropriate values in the private members. The DHT library reads temperature in degrees Celsius, so it needs to be converted to Fahrenheit when stored. Finally, these are the rather simple get functions to retrieve the last read temperature values. I use the fritzing tool to generate this diagram, which gives a more detailed look at how the hardware is configured. 5 volts are provided to the sensor and the button, where the button requires a 10 kilo ohm resistor on the ground pin. The signal pins of the sensor and button are wired to pins 12 and 2 respectively. Lastly, here's a graph generated with Google Sheets of the data collected for 5 minutes in my fridge and 5 minutes at room temperature. Since it's unknown how long it'll take for the temperature to stabilize, you can peek at the Arduino to see if the LED is lit, which tells you when the first 5 minutes of data was recorded. You then remove it from the fridge, press the button, and let it sit for another 5 minutes. And that's about it for this project. Thanks for watching, and let me know if you have any questions.